Now in this lecture we'll answer two questions. In the first question we find out the area of this rectangle ABCD, and in the second question we find out the area of this trapezoid ABCD. So we start with the first question. In the drawing we have a circle that is inscribed by this rectangle ABCD, or rectangle ABCD blocks this circle. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units. And again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside any rectangle are right angles. So this is a right angle. And we also know that the area of any rectangle equals to the length of the rectangle times the width. So we define the length of this rectangle ABCD as AB. And we define the width of this rectangle ABCD as AD. We will also define the radius of this circle as R. Point M is the point of tendency of tangent DC with this circle. Point N is the point of tendency of tangent AB with this circle. And point E is the point of tendency of tangent AD with this circle. Point O is of course the center of the circle, so we'll join points O and N together by straight line. Point O is the center of the circle, point N is the point of the circle itself. Therefore, ON is the radius of the circle that equals to R according to our definition. The radius ON that is equals to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by straight line. OM is of course the radius of this circle that is equals to R. Again, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. And finally, we join points O and E together by straight line. OE is of course the radius of this circle that is equal to R. The radius OE that is equals to R, the radius OE is drawn to point E, that is the point of tendency of the DA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, we can derive the small quadrangle DMOE. Inside the small quadrangle DMOE, we have 1, 2, 3 rectangles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. In the next step, we'll focus on the lower quadrilateral EO and A. In the lower quadrilateral EO and A, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the same rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So actually, the size of the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. The big angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment MON is a straight line. If line segment MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points, point M and point N, and therefore MN is a chord. MN is a chord that passes from point O, that is the center of the circle, and therefore we know that any chord that passes through the center of the circle must be the diameter of the circle. So write it down. MN is a chord that passes through the center of the circle that is to say for point O, and therefore MN is the diameter of the circle. MN is the diameter of the circle, so I write it down here, that MN is the diameter of the circle. So MN is the diameter of the circle, it is an absolute straight line. So actually this shape DMNA consists of 4 sides, 1, 2, 3, 4, and therefore shape DMNA is a quadrilateral. So write it down. Shape DMNA NA consists of 4 sides, and therefore it is a quadrilateral. It is a quadrilateral with 4 right angles. 1, 2, 3, 4. And according to rule 5, we know that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. And therefore, shape a quadrilateral DMNA is a rectangle because it has 4 right angles. According to rule 5. So I write it down here that DMNA, the big quadrilateral, is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. So write it down. In rectangle DMNA, side DA must be equal to the opposite side MN, according to the rule that the opposite sides of a rectangle are equal to each other. But according to our definition, DA is the width of rectangle ABCD, so we can write here that DA is the width of rectangle ABCD. And we just write now found out that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. In the next step, we will extend the radius EO of this circle that is equals to R by a straight line until it touches the circle. And we will find the touching point of the extended radius EO with this circle, this point is point L. The radius EO that equals to R, it is definitely a straight line. When you extend a straight line by straight line, the result is a straight line. So we extended the radius EO by straight line, the result is EL. Therefore EL is also a straight line, but EL is a straight line that touches the circle at 2 points, E and L, and therefore EL is a chord. EL is a chord that passes from point O, that is the center of the circle, and therefore EL is the diameter of the circle, because we know that any chord that passes through the center of the circle, must be the diameter of the circle. Therefore, EL is the diameter of the circle. So write it down, EL is the diameter of the circle. So we can add to this one equation that EL is the diameter of the circle, and from this equation, the width of rectangle ABCD equals to dA, and dA equals to mn, and mn is the diameter of the circle. This equals to EL. We will derive that EL is the width of rectangle ABCD. Okay, EL is the width. EL is also the width of rectangle ABCD. Okay. EL is actually the diameter of the circle, and it is also the width of rectangle ABCD. So in the next step, we will join points L and F together by straight line. By joining points L and F, we created peripheral angle EFL. This is peripheral angle EFL that subtends on EL, that is the diameter of the circle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. And therefore peripheral angle EFL must be equal to 90 degrees. So I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle. AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size according to this rule, rule 7. Actually, we have already implemented rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle EFL that subtends on EL, that is the diameter of the circle, and therefore peripheral angle EFL must be equal to 90 degrees in its size. So in the next step, we will extend, but before that we will define this angle, the circular angle ELEF as alpha. So in the right angle ELEF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this Ferguson angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll extend the diameter EL by straight line until it touches side CV of rectangle ABCD. But again, we'll extend the diameter EL of the circle by straight line until it touches side CB of rectangle ABCD. And we define the touching point of the extended diameter EL with side CB of rectangle ABCD. This point is point T. So EL as the diameter of the circle, it is absolutely a straight line. When you extend the straight line, the result must be a straight line. Therefore, we extended the straight line EL by straight line. We got ET must be also a straight line. Okay, so ET is a straight line. Therefore, by doing this construction, we can do quadrilateral ETBA. It is a quadrilateral because it has 4 sides. 1, 2, 3, 4. So, in quadrilateral ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore these 4 pieces again must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle in front of square. So we went to the big quadrilateral ETBA is a rectangle because it has 4 right angles. So I write it down. When the big quadrilateral ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So write it down. In the big rectangle ETBA, side ET must be equal to the opposite side AB. According to the rule that the opposite sides of a rectangle are equal to each other. But according to our definition, AB is the length of rectangle ABCD. So can I say that AB is the length of rectangle ABCD? And from this equation, ET equals to AB equals to the length of rectangle ABCD, we will derive that ET is also the length of rectangle ABCD. So if we found out that ET is the length of rectangle ABCD, we already found out that EL is the width of the same rectangle ABCD. EL is the width of rectangle ABCD. In the next step, we'll focus on the big right angle ETG. On the big right angle ETG, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we'll prove that the big right triangle ETG is similar to the small right triangle ELF. Actually, it is very easy to see it from the drawing, but I will prove it anyway. So why the right triangle ETG is similar to the small right triangle ELF? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, this is angle E, that is a common angle that belongs to both angles. Angle E belongs to the small right triangle ELF, and angle E definitely belongs also to the big right triangle ETG. So we can write down that angle E equals to itself as a common angle that belongs to both triangles. So in total, we have found out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of the small right triangle ELF. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle ETG is similar. This is the sign of similar to the right small triangle ELF according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side of unity CT. Over EF. EF equals to 12 units in its length according to what is given as the question. And it is equals to EG. EG in total equals to 12 plus 10, that is 22, over EL. EL is the missing side of unity cities. So in total, we found out that ET over 12 equals to 22 over EL. Here we will cross multiply this equation and we get that ET times EL is equal to 22 times 12. So ET times EL is equal to 22 times 12. 22 times 12 is 264. So in total, we found out that ET times EL is equal to 264. But we already found out that ET is the length of rectangle ABCD and EL is the width of rectangle ABCD. So we substitute ET by the length of rectangle ABCD and we substitute EL by the width of the same rectangle ABCD. So in total we get that the length of rectangle ABCD times the width of rectangle ABCD is equals to 264 square units. But what is the length times the width? Actually the length times the width of a rectangle is equal to the area of the rectangle. Therefore the length of rectangle ABCD times the width of rectangle ABCD is equal to the area of rectangle ABCD. So if you found out that the area that we're looking for this question, that is the area of the big rectangle ABCD, is equal to 264 square units. And that is the answer to the first question. Repeat again, if we found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square units. So we finish with the first question. In the next step, I will present to you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. It is given us the question that AB equals to AP, PD equals to DC, line segment BQ equals to 4 units in its length, line segment QC equals to 9 units in its length. This is angle PQC, that is a right angle, and those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So first of all, we know that AB equals to AP. So we define the length for side AB as A. And again, the length for side AB equals to A units according to our definition. If AB equals to A, then AP must be also equal to A because they are equal to each other. We know that PD equals to DC according to what is given in the question. So if we define the length of side PD as B, that is to say side PD equals to B units in its length according to our definition, then the length of side DC must be also equal to B units because they are equal to each other. In the next step, we'll join points B and P together by straight line. And we'll also join points P and C together by straight line. By joining points B and P, we created the right small triangle PAB. The right small triangle PAB is also an associated triangle because AP equals to AB. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and it is also true, therefore it is true in the right triangle ABP. So which angles we have in the right triangle ABP? We have this angle is a right angle, plus alpha is 180 degrees. So I write it now. In the right triangle ABP, the sum of the angles must be equal to 180 degrees. That is to say 90 degrees plus 2 alpha. In total, the sum of those three angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we divide this equation by 2 and finally we get that alpha equals to 90 degrees over 2 is 45 degrees. So this is angle alpha that is equal to 45 degrees in its size. This is also angle alpha that is equal to 45 degrees in its size. From this specific example, we can conclude that any right triangle that is also an associated triangle will have always the same three angles. One angle will be a right angle because it is a right triangle, and the other two angles, each of them will be equal to 45 degrees. Why? Because of the fact that it is an associated triangle. Because of the fact that it is an associated triangle, those two angles must be also equal to each other. Each angle must be equal to 45 degrees in its size. And therefore, we have here the right triangle PDC. It is also an associated triangle. Why the right triangle PDC is an associated triangle? Because side PD equals to side DC. So this is the right triangle PDC that is simultaneously a right triangle and also an associated triangle. And therefore, those two angles must be equal to 45 degrees each of them. We also have to repeat on the same proof that those two angles must be equal to 45 degrees. Because it will be exactly the same proof. This angle equals to 45 degrees in size, and this angle also equals to 45 degrees in size because of the fact that triangle PDC is an isosceles and right triangle simultaneously. So we know that AD is one side of trapezoid ABCD, and therefore it is absolutely a straight line. So if you focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees. According to rule 3, that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees. In total they are equal to 90 degrees. So 90 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to rule 3. Okay, therefore this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is equal to 180 degrees. That is the sum of the angles on the right side of the straight line AD at point P according to rule 3. We define the size of this small angle BPQ as alpha. So if this angle equals to alpha, then this missing angle, that is to say angle PQ angle QPC must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. It is equal to 90 degrees. So in the right big triangle PQC, this angle equals to 90 degrees minus alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We know that side BC, that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3, that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point Q? We have this angle that is a right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right small triangle PBQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll prove that the small green right triangle PBQ, this green right triangle PBQ, is similar to the big right triangle PQC according to angle similarity rule. Actually, it is very easy to see it from the drawing, but I will prove it anyway. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we should prove that all the three angles of the big right triangle PQC, this big right triangle PQC, are correspondingly equal to all the three angles of the small green right triangle PBQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually proved that the big right triangle PQC is similar, this is the sign of similar, to the right small green triangle PBQ according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But before that, it is very easy to see that PQ is a common side that belongs to both triangles. PQ belongs to the green triangle PQB, and PQ also belongs to the big right triangle PQC. So PQ is a common side that belongs to both triangles. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. So I repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. PQ is the missing side, so we leave it as it is. Over BQ, BQ equals to 4 units in its length according to what is given as the question. And it is equal to QC. QC equals to 9 units in its length, also according to what is given as the question, over PQ. PQ is the missing side, so we leave it as it is. So in total, if you found out that PQ over 4 equals to 9 over PQ. Here we will cross multiply this equation and we get that PQ times PQ is PQ squared, and it is equal to 9 times 4, that is 36. So PQ squared equals to 36. Here we will take a root out of this equation, and finally we get that PQ equals to the square root of 36, that is 6. So if you found out that the missing side PQ is equal to 6 units in its length. This is the missing side PQ that is equal to 6 units in its length. In the next step, we will implement the Pythagoras theorem of the big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. In the right big triangle PBC, BC is the hypotenuse, and therefore the square of the hypotenuse is BC squared, and BC squared must be equal to BP squared plus PC squared. Repeat again, according to the Pythagoras theorem, in this right big triangle PBC, BC squared, that is the square of the hypotenuse, must be equal to BP squared plus PC squared. BC in total it is equal to 9 plus 4, that is 13, therefore BC squared is 13 squared, that is 169. it is equal to BP squared. What is the value of BP squared? In order to find out the value of BP squared, we will implement the Pythagoras theorem on the right small triangle, triangle PAB. According to the Pythagoras theorem in the right small triangle PAB, a squared plus a squared equals to BP squared. So BP squared in total equals to a squared plus a squared, that is 2a squared. BP squared equals to 2a squared plus PC squared. What is the value of PC squared? In order to find out the value of PC squared, we will implement the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem on the right triangle PDC, B squared plus B squared equals to PC squared. So in total PC squared equals to B squared plus B squared, that is 2B squared. So PC squared equals to 2B squared. So in total we found out that 169 equals to 2A squared plus 2B squared. So 169 equals to 2a squared plus 2b squared. So here we'll take 2 as a common factor from those two expressions. Inside the brackets we left only with a squared plus b squared. So in total we found out that 169 equals to 2 times a squared plus b squared. Here we will divide this equation by 2 and finally get that a squared plus b squared is equal to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, we have a special formula for the area of any trapezoid, but we will not use the special formula. We find the area of trapezoid ABCD in a different way. Actually, the area of trapezoid ABCD is equal to the sum of the areas of the three components that the trapezoid ABCD consists of. Trapezoid ABCD consists of the first component is the right triangle ABP. So this, I write it here. This is the first component. The second component that trapezoid ABCD consists of is the big right triangle PBC. So write it down. This is the second component. And finally, the third component that trapezoid ABCD consists of is the right triangle PDC. So write it down. This is the third component that trapezoid ABCD consists of. So it is very easy to see that the sum of the areas of those three components must be equal to the area of the big trapezoid ABCD. So the area of trapezoid ABCD must be equal to the area of the first component. What is the area of the first component? Actually it is the area of the right small triangle ABP. Plus the area of the second component that trapezoid ABCD consists of. The second component, it is actually the area of the big right triangle PBC. Plus the area of the third component that trapezoid ABCD consists of. What is the area of the third component? It is actually the area of the right triangle PDC. So if it again, we shall find out that the area of trapezoid ABCD is equal to the sum of the areas of the three components that trapezoid ABCD consists of. The first component is the right triangle ABP, so it is the area of the right small triangle ABP. plus the area of the second component. The second component is the right big triangle, triangle PBC, so it is plus the area of the second component, that is the area of the right big triangle, triangle PBC, plus the area of the third component, that is actually the area of the right triangle PDC. And again, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. So we'll find out the area of each component separately, and then we'll add the three areas together. The result will be the area of trapezoid ABCD, that is the area that we're looking for in this question. So what is the area of the first component? It's actually the area of this small right triangle APB. Actually, we know that the area of any triangle is equal to the base of the triangle times the height over 2. We choose the base as AB, therefore the height will be AP over 2. AB is A, times the height AP, that is also A, over 2. AB is, so 8 times A is A squared over 2. So in total, we actually found out that the area of this first component is actually equals to A squared over 2. So we can write here also that the area of this first component is A squared over 2 plus the area of the second component, that is actually the area of the big right triangle PBC. The big right triangle PBC consists of also the green triangle. So what is the area of the big right triangle PBC? Will be equal to the base of the triangle, that is BC, times the height, that is QP. Why QP is the height? Because it creates 90 degrees with the base BC. Those two angles are right angles. So the height is QP divided by 2. So total, if you found out that the area of the second component, that is the area of the big right triangle PBC, is equals to the base BC times the height QP over 2. So I write it down here. The area of the second component, that is the area of the big right triangle PBC, it is equals to the base BC times the height QP over 2. Plus the area of the third component, the triangle that trapezoid ABCD consists of, it is actually the area of the right triangle PDC. The area of this right triangle PDC is equal to the base DC times the height DP over 2. The base DC is B times the height DP, that is also B over 2. So it is B times B, that is B squared over 2. So in total, if you found out the area of the first component is B squared over 2. B squared over 2. So here we have A squared over 2 plus B squared over 2 is A squared plus B squared over 2. We took 2 as a common factor from those two expressions. Plus the area of the big right triangle PBC, that is actually BC. BC, in total it is 4 plus 9, that is 13. Times QP. QP is 6 divided by 2. So in total, the area of the big right triangle PBC, it is equals to 13 times 6 over 2. Okay, so here we have the area of trapezoid ABCD in total, it is equals to A squared plus B squared over 2 plus 13 times 6 over 2. So it is equals to A squared plus B squared over 2. What is the value of this expression? It is actually equals to 6 over 2 is 3, and 3 times 13 is 39. So in total, the value of this expression is 39 square units. So actually found out that the area of trapezoid ABCD is equals to a squared plus b squared over 2. But we already found out that a squared plus b squared equals to 169 over 2. Therefore, we substitute a squared plus b squared in this expression by 169 over 2. So a squared plus b squared equals to 169 over 2, and we have to divide it by 2 again. Plus 39. So total the area of trapezoid ABCD equals to 169 over 2 times 2. 2 times 2 is 4, plus 39. So the area of trapezoid ABCD in total it is equal to 169 over 4 plus 39. Here we multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number. And we get that in total in the numerator we have 169 plus 39 times 4 is 156. So in total in the numerator we have 169 plus 169 plus 156 over 4. 169 plus 156 is 325 over 4. So in total, if you found out that the area that we are looking for in this question, that is the area of trapezoid ABCD, it is equal to either 325 over 4 square units, so in terms of numbers, it is equal to 81.25 square units. So, write it down. If you found out that the area of trapezoid ABCD is equal to either 325 over 4 square units, so in terms of numbers it is equal to 81.25 square units. That is the answer to the second question. So in the next step, I summarize the lecture. We start with the first question, of course. In the first question, our task was to find out the area of this rectangle ABCD. So in the drawing, we have a circle that is described by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FQ, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles in any rectangle are right angles. So this missing angle is a right angle. And we also know that the area of any rectangle equals to the length of the rectangle times the width. We define the length of this rectangle ABCD as AB and the width as DA. We define the radius of this circle as R. We join points O and N together by straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of the circle. That is equal to R according to our definition. The radius ON, that is equal to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by straight line. OM is of course the radius of the circle, that is equal to R. The radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. And finally, we join points O and E together by straight line. O here is of course the radius of the circle, that is equals to R. The radius OE that is equal to R, the radius OE is drawn to point E, that is the point of tendency of tangent DA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule 1. By doing this construction, we created the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 2 fair right angles. The sum of right angles is 270 degrees, so 270 degrees plus the size of this four-facing angle, in total it must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this four-facing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral EONA, we have 2 free right angles. The sum of we have 2 free right angles. The sum of free right angles is 270 degrees, so 270 degrees plus the size of this four-facing angle, in total it must be equal to 360 degrees, according to the sum rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this four-facing angle must be equal to 90 degrees in its size. So we found out that the size of the big angle MON is 90 degrees plus 90 degrees, that is 180 degrees. The big angle MON is equal to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line segment MON is a straight line. If line segment MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points, M and N. And therefore, MN is a chord. MN is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. So again, if we found out that MN is the diameter of the circle. Anyway, MN is a diameter, it is absolutely a straight line, and therefore, in quadrilateral DMNA, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this right angle in front of square. So let's do the big quadrilateral DMNA is a right angle because it has 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, again in the big rectangle DMNA, side MN must be equal to the opposite side DA. But according to our definition, DA is the width of rectangle ABCD, so we can write here that DA is the width, and we just write off, found out that MN is the diameter of the circle. So we can write here that MN is the diameter. In the next step, we extended the radius EO, that is equal to R. We extended the radius EO by a straight line until it touches the circle at this point. We define the touching point of the extended radius EO with this circle. This point is point L. Actually, when you extend the straight line by straight line, the result is a straight line. So EO is a straight line. We extended the radius EO by a straight line, and therefore the result EL must be also a straight line. So EL is a straight line that touches the circle at 2 points, E and L. Therefore EL is a chord that passes from point O, that is the center of the circle, and we know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore EL is the diameter of the circle. So can I tell that EL is the diameter of the circle, and from this equation, long equation, the width equals to DA equals to MN equals to the diameter equals to EL, we will derive that EL is also the width of rectangle ABCD. EL is the width of rectangle ABCD. Okay, so in the next step, we join points L and F together by a straight line. By joining points F and L, we created peripheral angle EFL. This is peripheral angle EFL that subtends on EL, that is the diameter of the circle, and according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. Therefore, peripheral angle EFL is equal to 90 degrees in its size according to rule 7. Okay, so in the right triangle EFL, we define this angle as alpha, so this angle equals to alpha according to our definition, alpha plus 90 degrees. So this is angle alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we extended the diameter EL of the circle by a straight line until it touches side CB of this rectangle ABCD. Again, we extended the diameter EL by a straight line until it touches side CB of this rectangle ABCD. And we define the touching point of the extended diameter EL with side CB. This point is point T. Again, when you extend EL as a diameter, it is absolutely straight line. When you extend the straight line by straight line, the result is a straight line. We extended the straight line EL by straight line, the result ET must be also a straight line. And therefore we created the quadrigonal ETBA. Inside quadrigonal ETBA we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this fourth missing angle, in total it must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrigonal is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. Okay, so inside the quadrigonal ETBA we have 4 right angles, and according to rule 5, any quadrigonal that has 4 right angles must be this rectangle, if not a square. Therefore, we relate to the big quadrigonal ETBA, it's a rectangle because it has 4 right angles. So quadrigonal ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. Repeat again. In rectangle ETBA, the opposite sides must be equal to each other. That is to say, side ET must be equal to the opposite side AB. In rectangle ETBA, side ET must be equal to the opposite side AB. But according to our definition, AB is the length of rectangle ABCD. So we can write here that AB is the length of rectangle ABCD. And from this equation, ET equals to AB equals to the length of rectangle ABCD, we will derive that ET is also the length of rectangle ABCD, and we have only found out that EL is also is the width of the sub-rectangle ABCD. Okay. In the next step, we focus on the big right triangle ETG. On the big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Actually, it is very easy to see that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. Anyway, I hope those two right triangles are similar to each other. First of all, this is angle E, that is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E definitely belongs to the big right triangle ETG. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So in total, if we found out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of the right small triangle ELF. And therefore those two right triangles are similar to each other according to angle similar to rule. So if again we found out that the big right triangle ETG is similar, this is the sign of similar, to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. Again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EF of the small side EL of the small right triangle ELF. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. Over EF is 12 units in its length according to what is given as the equation, and it is equal to EG in total is 12 plus 10, that is 22. Over EL is the missing side, so we leave it as it is. So in total we should find out that ET over 12 equals to 22 over EL. Here we cross multiply this equation and finally found out that ET times EL equals to 22 times 12. So ET times EL equals to 22 times 12. 22 times 12 is 264. So if we found out that ET times EL equals to 264. But we have only found out that ET is the length of vertical ABCD and EL is the width of vertical ABCD. So we can substitute ET by the length and EL by the width. So in total we found out that the length of vertical ABCD times the width of vertical ABCD is equal to 264 square meters. And that is the answer to the first question. Repeat again, we found out that the length of this vertical ABCD, that is the area, we found out that the area of this big rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square meters. We finished with the first question. In the next step I presented to you the second question, and we solve the second question of this lecture. The second question, our task is to find out the area of this trapezoid ABCD. It is given as the question that AB equals to AP, PD equals to DC, BQ is 4 units, measurement QC is equal to 9 units in its length. This is angle PQC, that is the right angle. Those two angles are also right angles. Again, our task is to find out the area of this trapezoid ABCD. So, first of all, AB equals to AP. So if we define the length of AB as A, then AP must be also equal to A because they are equal to each other. Likewise, PD equals to DC. So if we define the length of PD as B, then DC must be also equal to B because they are equal to each other. In the next step, we join points P and B together by straight line, and points P and C together by straight line. By joining points P and B, we get the right small triangle, triangle ABP. In the right small triangle, triangle ABP, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other. So if we define this angle as alpha, this angle must be also equal to alpha because they are equal to each other, according to the rule that I mentioned. So the sum of the angles in any triangle is 180 degrees, and especially it is true in the small right triangle ABP. So which angles we have in the small right triangle ABP? We have this angle that is 90 degrees, plus alpha is 180 degrees. So in the right triangle ABP, 90 degrees plus 2 alpha equals to 180 degrees. Subtract the 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees, we divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equals to 45 degrees in its size. This is also angle alpha that is equals to 45 degrees in its size. So we found out that in any right triangle that is also an isosceles triangle, we will always have the same three angles. One angle is the right angle, and the other two angles, each of them is 45 degrees. And because of the fact that triangle PDC is a right triangle and also an isosceles triangle, we have the same three angles. Here this angle is right angle, those two angles must be also equal to 45 degrees each of them. So we have here AD is one side of trapezoid ABCD, therefore it is absolutely straight line. So if we focus on the right side of the straight line AD, it's point P. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AD of point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees. In total it is 90 degrees. So 90 degrees plus the size of this third missing angle, in total must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees in total equals to 180 degrees. That is the sum of the angles on the right side of the straight line AB at point P according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. That is to say the missing angle BPC must be equal to 90 degrees in its size. So if we define the size of the small angle BPQ as alpha, then the size of the missing angle QPC must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. Okay? because the missing angle here must be equal to 90 degrees minus alpha. This is actually angle QPC. So in the right angle QPC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, the 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in an triangle. BC is one side of trapezoid ABCD, therefore it is absolutely straight line. So if you focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the left side of BC at point Q? We have this angle that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right range triangle BPQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this further angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that the small green triangle BPQ is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So I shall prove that all the three angles of the big right triangle PQC are correspondingly equal to all the three angles of the green right triangle PPQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. So if again, I shall find out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. But before that, PQ is the common side that belongs to both triangles. It belongs to the green triangle PBQ, and PQ also belongs to the big right triangle PQC. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. Again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the right triangle PQC of the side PQ of the right small triangle PBQ. PQ is the missing side, so we leave this it is over PQ. PQ is 4, and it is equals to QC. QC is 9 over PQ. PQ is the missing side, so we leave this it is. So in total, we found out that PQ over 4 equals to 9 over PQ. Here we must multiply this equation, and finally found out that PQ times PQ is PQ squared. PQ squared equals to 9 times 4, that is 36. PQ squared equals to 36. We took out of this equation and finally found out that PQ equals to the square root of 36, that is 6. In the next step, we implemented the Pythagoras theorem of the big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle PBC, BC is the hypotenuse, and therefore, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, must be equal to BP squared plus BC squared. Again, BC squared, that is the square of the hypotenuse, must be equal to BP squared plus BC squared. BC in total is 4 plus 9, that is 13. Therefore, BC squared is 13 squared, that is 169. BC squared is 169, and it is equal to BP squared. What is the value of BP squared? In order to find out the value of BP squared, we implemented the Pythagoras theorem on the right small triangle PAB. According to the Pythagoras theorem on the right small triangle PAB, A squared plus A squared equals to BP squared. So in total, BP squared equals to 2A squared, BP squared equals to 2A squared, plus PC squared. What is the value of PC squared? In order to find out the value of PC squared, we implemented the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem on the right triangle PDC, B squared plus B squared equals to PC squared. So total PC squared equals to 2B squared. Yeah, PC squared equals to 2B squared. So in total, we found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, here we took two second factor from those two expressions, so inside the brackets we left with only a squared plus b squared. So in total, we actually found out that 169 equals to 2 times a squared plus b squared. Here we divided this equation by 2, and we found out that a squared plus b squared equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. Actually, the area of trapezoid ABCD is equal to the sum of the areas of the three components that it consists of. Trapezoid ABCD consists of three components. The first component is the right small triangle ABP, the second component is the right big triangle PBC, and the third component is the right big triangle PDC. Repeat again, the area of trapezoid ABCD equals to the sum of the areas of the three components that it consists of. 1, 2, 3. Again, the area of trapezoid ABCD equals to the sum of the areas of the three components that it consists of. So we find out the area of each component separately, and then we add the three areas together. The result must be the area of trapezoid ABCD. So what is the area of the first component? Is actually the area of the small right triangle ABP. The area of this triangle, the area of any triangle equals to the base of the triangle times the height over 2. The base is AB times the height, that is AP over 2. So it is A times A, that is A squared over 2. So the area of the first component is A squared over 2, plus the area of the second component, that is the area of the big triangle PBC. It is actually the base PC times the height QP over 2. So the area of the big right triangle PBC, it is equals to the base BC times the height QP over 2, plus the area of the third component, that is actually the area of this triangle, the right triangle PDC. It is equals to the base DC times the height DP over 2. DC is B times DP, that is also B, so it is B times B over 2. This is actually B squared over 2. The area of the third component is B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. BC is 13, QP is 6 divided by 2. So in total, we found out that the area of trapezoid ABCD equals to A squared plus B squared over 2, and 13 times 6 over 2 is 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. So the area of trapezoid ABCD equals to A squared plus B squared over 2 plus 39. But we already found out that A squared plus B squared equals to 169 over 2. Therefore, we can substitute A squared plus B squared here by 169 over 2. And we have to divide it by 2 again. So it is 169 over 2 times 2. Plus 39. So it is 169 over 2 times 2 is 4. So it is 169 over 4 plus 39. Here we multiply 39 by 4, and then we divide it by 4 in order to make a common factor of this number. So in total, in the numerator we have 169 plus 39 times 4, that is 156 divided by 4. 169 plus 156 is 325 over 4. 325 over 4 is equal to 81.25 square units. So in total, we should find out that the area of this trapezoid ABCD is equal to either 325 over 4 square units, or in terms of numbers, it is equal to 81.25 square units. Okay, thank you very much.